I sort of just want to, it's a nice transition from shape of molecules. How do we get this shape? And so understanding how these orbitals arrange themselves when they're no longer in atoms, but now in molecules, is a good way to understand how these shapes occur. And then once we get through that, I'm going to skip 6 and 7 because they're mostly on stoichiometry, and we've done a lot of stoichiometry. I think you would agree. And then we'll go to gas laws. So we'll probably be into gas laws maybe tomorrow or possibly on Monday. So hopefully that'll make the lab we did today, hopefully will make a little bit more sense when we start looking at the gas laws in the lecture as well. So I'm going to sort of pick up where we left off on shapes. So we looked at some of the simpler shapes, depending on how many areas of electron density there are around a central atom. We pretty much figured out that, yeah, if there's 2 areas of density around an atom, yeah, they're going to move away from each other as much as they can, and you're going to get a linear shape. That made sense. And then if we have 3 areas of electrical density around a central atom, they're going to move to make a triangle and be 120 degrees apart from each other in a plane, in a 2-dimensional plane, because that's as far away as they can get away from each other. And then it gets a little more complicated when we get to 4, 5, and we'll see we even have like 6 areas of electron density. How would we deal with those? And so we sort of left off with 5. So when you have 5 regions, and so you can see here, remember that we talk about both the bonds or electron dense area, because bonds are made of shared electrons, and these free lone pairs, like these 2 here. So remember, we count all of them as one area. So here, when we have 5 areas around it, we call these trigonal bipyramidal. And you don't have to remember these names are kind of silly, because you'll be able to refer to these tables. But what I want you to take away is that the overall molecule's shape looks different depending on how many bonds and how many electron pairs, but the overall shape of the molecule is the same. They have this particular shape here, where we have an up and down axial right through the main atom. And then we have a triangle around the outside, and that's where you get the trigonal bipyramidal description of it. So we have the axial positions on the top and the bottom, and then around the equator, we have a triangle. And so if it's all atoms, you get that particular shape. If you replace one of the atoms with a lone pair, you can see we still get the same overall shape, but we don't really see the electrons as far as the molecular shape goes. And so it looks like a seesaw a little bit, and we actually call it seesaw shape. If we replace 2 of the bonds with lone electron pairs, it looks like a T, because the overall molecule sort of just looks like that. And you don't really see the 2 lone pairs that are spinning around what we call the equatorial positions. And then finally, if we have 3 lone pairs and 2 atoms, you'll see we have the atoms go to the top and the bottom, and the electrons go around the outside. And that's because you remember that lone pairs of electrons are highly negative, and they repel each other much more than just bonded atoms do. And so the most stable arrangement in this particular situation is to get those lone pairs as far apart from each other as possible. And the farthest distance you can get apart from each other in this particular arrangement is along the equator, where they can be 120 degrees away from each other. If you put one of them at the top, remember this angle there is 90 degrees. So that wouldn't be as stable. You get a lot more repulsion due to those lone pairs being there. So these are the difference, as I sort of just showed you a minute ago, between the axial and equatorial. Axis, just think of it as the axis of the Earth, North Pole and South Pole. We got the axis. And then around the middle, we have the equator. Same thing here. So when we're making or drawing a molecule, we try and put the lone pairs in equatorial positions, if at all possible, because that separates them from each other as much as possible. So equatorial repulsions are weaker because they're further away, because we have this 120-degree angle between the equatorial positions, and we have a 90-degree angle between the axial and equatorial positions. So if you have something that's really, really repelling, strongly repelling other atoms and other electrons, that's where you want to stuff it, in the equatorial position. And then when we get 6, then things start getting really weird. But at least it's easier to say this time. Octahedral, that's much easier to say than bipyramidal, axial bipyramidal. So here, when we have 6 atoms or 6 electron groups circulating an atom, a central atom in the middle, we call it octahedral. And when they're all present, we have AX6. Remember, X stands for the number of atoms, and E stands for the number of lone pairs. We have an octahedral, and all the angles are 90 degrees. Every angle is 90. When we replace 1 with a lone pair, we have this sort of square shape. We sort of have this cross and an atom coming out. We call that a square pyramid shape, because it kind of looks like a pyramid there, but square. And then finally, if we replace 2 of the atoms with lone pairs, it basically looks planar. But it looks like a square this time, because we have 1, 2, 3, 4 atoms surrounding the central atom, and they're all in the same plane. So they would look two-dimensional. Okay? All right. Let's get to the good stuff. So remember, there's different shapes depending on what period your central atom is in. If it's in period 2, and those would be things like nitrogen and carbon and oxygen. Those can only form 4 bonds total. And so we don't have any of these like more bizarre shapes. They only have 4 areas of electron density around them. But when you get down to periods 3 through 6, you start getting things like sulfur and phosphorus. They can adopt a lot more electrons, because remember, they now have a d orbital in their outermost shell. There's room for lots more electrons than just 8. And so you can adopt 4, 5, 6 different regions of electron density. These were 1, 2, 3, and 4. And these sort of made sense. I want to sort of just pay attention a little bit to the angles, because we're going to be doing a little bit of that tonight. So the angles, when you have a triangle, are pretty straightforward, 120 degrees. And when it's tetrahedral, like this, the ideal angle is 109.5. So what we're going to be doing is making some of these structures, excuse me, and seeing how far, whether we can predict if they're going to deviate from 120 and 109. Are they going to be more? Are they going to be less? And we should be able to make those predictions based on what the groups are around the around the central atom. Okay. Here's our 5 and 6. So these are the steps for taking a formula and then converting it to a shape. So you get the molecular formula, whatever it is. Let's say it's carbon tetrafluoride. So that's my formula. Now I need to make a Lewis structure out of it. So we just do it like we've been doing before. We count all the valence electrons. Which atom will be put in the middle, this particular formula? I've got a carbon and 4 fluorines. Which one goes in the middle?
Carbon.
Carbon. Carbon almost always goes in the middle because carbon likes making lots of bonds. Carbon generally always makes 4 bonds. It doesn't have any lone pairs. So carbon is like a natural for going in the middle of a molecular formula. So we just put carbon in the middle, surround it with the fluorines, and then we count up all the electrons, and then we decorate our drawing with the electrons in, and then we count how many how many bonding groups are around and how many lone pairs are around. In this particular instance, how many electron groups surround the carbon? So carbon is my central axis. So we put down A, and then for X, what would we put down? How many bonding groups are around it? How many areas of electron density? First of all, how many areas of electron density would be around carbon with this particular shape? With that particular arrangement?
4?
4. It's got 4. So how many are bonding and how many are lone pairs?
4 bonding and 0 lone pairs.
Exactly. So we'd say X, how many atoms are around? Basically, how many bonding pairs do we have? It's 4. And we don't have any free electrons. So basically what we would do is then just look on our table, AX4, what shape is that? And we'd see it's tetrahedral. So let's try a couple. So we're going to draw phosphorus trifluoride, and we're going to draw COCl2, and I'll show you what that looks like. So first, TF3, so let's draw that one. So who goes in the middle, phosphorus or fluorine?
Phosphorus.
Phosphorus, that's right. So we put phosphorus, there we go. So we put phosphorus in the middle, and then I put fluorine around it. So, and remember, we put a single bond between each one just to start. It's got to be bonded. So how many total electrons are we dealing with? How many valence electrons does phosphorus have? Got to have a periodic table in front of you at all times.
5.
5, that's right. So one phosphorus has 5 electrons, and we have 3 fluorines, and how many do they have?
7.
7. So 21 and 5, that's 26 electrons. And how many have we used in bonds?
6.
That's right. Got 1, 2, 3, 4, 5, 6. Remember, each bond is a pair. So we don't have 26 left over, we got 20 left over. So as usual, we just go around and decorate the exterior first and then move. If there's any electrons left, we go into the middle. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Got 2 left. Where do we put them?
Phosphorus.
On phosphorus, exactly. And then we look at it, so does that make sense? Now, we count the number of valence electrons everybody has, because you want to see if there's any charges in this particular structure.
No
So let's do that. So how many valence electrons should phosphorus have? We already answered that. It's 5. How many does it have?
5.
It's got 5, right? It's got 1, 2, 3, 4, 5. So there's no charge on phosphorus. What about fluorine? It's supposed to have 7 electrons. How many does it actually have?
7.
Actually has 7 as well. So it's got the 6 in lone pairs and that 1. So 7, 0. So there's no charge on anybody. And that makes sense because fluorine basically always looks like this. Fluorine is always going to have 6 electrons in a bond. You remember when we draw these things, when we put the dots around it for the Lewis structure, fluorine is 1, 2, 3, 4, 5, 6, 7. So it has those 3 lone pairs and 1 for sharing. Phosphorus, we go around 1, 2, 3, 4, 5. It has 1, 2, 3 lone electrons for sharing and a lone pair it keeps for itself. And that's exactly the structure we have here. So what would we call, so when we want to figure out what shape it's going to be, we do the AX test. A, X, E. So A is our central atom. So what's X?
3.
3. And E?
2. Or is it 1?
It's 1. It's for each pair.
Oh, it's
It's
1.
for each pair. Because these two numbers, 3 and 1, should equal the number of areas of electron density. We've got 1, 2, 3, 4. So AX3E1. And so we would look that up and we would see what shape that is. So there we go. So we have the right shape. We see that it's tetrahedral. Got 3 bonding groups. And yeah, what I did forget to do was see if you could predict what the bonding was. And from here, we see that because there's a lone pair pushing these fluorine atoms away from it, that the angle between the fluorine atoms will be less than 109.5, because it actually pushes down from the top and sort of squeezes them a little closer together. So instead of 109, we actually have 96, actually pushes them in about 13 degrees. So you can see that one lone pair has pushes pretty hard. It repulses other electron groups away from it, and really has a very strong effect on the lone pairs. It has a strong effect on the shape of these molecules. And since it has such a profound effect on the shape of the molecule, it's also going to have a profound effect on the polarity of the molecule, because we know that polarity and shape are intricately bound. You can't separate one from the other. Let's try another one. So COCl2, I'll show you how that works, how that's put together. It's an organic compound. You're all going to be doing organic next, right? So it goes like this. We have a carbon here, oxygen there, chlorine, chlorine. So single bond. So how many electrons, valence electrons in carbon?
4.
4. So carbon, 4. And oxygen?
6.
6. And chlorine?
7.
7. There you go. So we got 14 and 6 is 20 and 4. So 24. We do 24 electrons go around. And how many have we used in bonds? 6.
18.
So Got 18 left. So 18 left over. So as usual, decorate the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, that's all of our electrons. So now we need to check to see what our charges are. Because I'm out of electrons. I don't have any to put in the middle. So what is going to be my charge on the chlorines?
Got it.
Chlorine has 7 valence electrons. 7 valence electrons. And I'll subtract how many it actually has. How many does it actually have in this model?
It actually has 7.
It actually does have 7, right? It's got the 6 that it has for itself, and it's sharing 2, and it gets to keep half of that. So it has 7. So there's no charge on chlorine. Now, what about oxygen? What's going to be the charge, if any, on oxygen?
Negative.
Oxygen has 6 valence electrons. And how many does it have in this particular model?
7.
It also has 7, because it looks just like chlorine. So if chlorine has 7, oxygen's got to have 7 too. So it has 7 as well.
It's a -1 charge.
Yeah, so we're going to have a charge on oxygen here, -1. And what is my charge on carbon? How many valence electrons is carbon supposed to have?
4.
4. It's supposed to have 4. And how many does it have?
3.
3. It's only got 3. It's only making 3 bonds. So it gets to keep 1 electron from each one, and it doesn't have a lone pair. And carbon rarely, if ever, has a lone pair. Actually, it does sometimes, but very rarely. So here, it doesn't have any. It's only got those 3. So what's the charge on carbon?
+1.
+1. Uh-oh. See, that's going to be an issue because I've got a minus charge right next to a positive charge. When that happens in our molecule, what generally will happen to the electrons?
Double bond the oxygen and the carbon.
Yeah. A pair of those electrons, one of those lone pair on the electrons, on the oxygen will move and make a double bond. And when it does, that gives this particular oxygen 6 valence electrons because it has the 4 that are in lone pairs and it has 2 bonds. So it gets to keep one from each bond. So it's got a total of 6. So now there is no charge on oxygen. And carbon now has 4 bonds, which it almost always makes. And it gets to keep 1 electron, gets to claim 1 electron from each one. And so now it is no longer charged. It has its 4 valence electrons. So it isn't charged either. So this is the correct drawing, the correct representation of this particular molecule. Now, let's do the Axe test. What is our central atom here? Who's our central atom?
Carbon.
Carbon, right. So when I do my AXE, I'm talking about carbon. So how many areas of electron density surround that carbon?
Four.
So you think each of the bonds is an area of electron density, right?
Yeah.
That is usually true, but since we have a double bond here, the double bond is in the same area of space because I've got my carbon and my oxygen are bonded to each other. And the next chapter will show you how that happens. So we got the carbon and the oxygen bonded to each other, and they're sharing 4 electrons, basically in the same space where there were 2 electrons for a single bond. So we really only consider it an area of it's only one area of electron density. It's a higher density, I will grant you that, but it's still one area of electron density. So the answer is 3. It has 3 areas of electron density around it, all bonding. So my X is 3, because there's 3 bonding regions. And how many lone pairs does carbon have on it?
None.
Bupkis, and rarely does. So put a 0 there. So AX3, now if you remember, what shape was that? 3
Trigonal.
regions. What was it?
Trigonal.
Yeah, it was trigonal planars. It looks like a triangle. And so these bonds should all be 120 degrees. But remember, they're only 120 degrees if everything surrounding that carbon is identical. Now, in this instance, they're not identical, are they? Because we have 2 chlorines and a double bonded oxygen. So my question to you is, what is going to be that angle between the 2 chlorines? This angle right here. That bond. Is it going to be more than 120 degrees, or is it going to be less than 120 degrees? Are those chlorines going to be pushed together, or are they going to be further apart? What do you think?
Less than 120?
Less than 120. Okay, why do you say that?
Because I would think that the electron density between carbon and oxygen is so high that it's repelling more.
Oh my God. You know how right you are? That is exactly right. It's like I sort of mentioned a minute ago. If you have a double bond in space, that's twice the concentration of electrons as a single bond. That's 4 of them, right? And so if a single pair of electrons is repulsive, 2 pairs of bonding electrons are even more repulsive. So you're absolutely right. This double bond is a high electron density and pushes this carbon away, this chlorine away, and pushes that chlorine away from itself. So this angle will be less than 120 degrees. Dang, we should be teaching this class. I'm going to take some days off. So here, let's have a look. Yeah, so see, this is our grouping, just so we have the right shape. And since the double bond has a lot of electron density, it pushes the chlorines together a little bit. So instead of it being 120 degrees, it pushes it together about 9 degrees more. So now it's 9 degrees less, so it's about 111 degrees. And so we use this kind of information to see how repulsive lone pairs, double bonds, and triple bonds actually are, because we can measure these things very accurately. So great job.
Professor, I have a question.
Yep, sure.
On the exam, are we gonna be finding angles? Like the degree of the angle?
No, not the exact. No, there's no way you would know the exact angle. That's impossible. But I will be able to ask you, is it going to be less than the ideal angles? Because the ideal angle will be given with the table. So the table, all you need to do, the only thing you need to know is how to do the ACTS test. So how many electrons are in bonds around the central atom, and how many free lone pairs of electrons are around the atom. Figure out what your AXE is. Let's say it's 3 and 2. So then you just look up, okay, what shape is that? And you look up what shape it is, and it gives you all the angles, what the ideal angles would be. And then I would ask you, well, based on those ideal angles, with these particular atoms surrounding it, is it going to be less than the ideal or more than the ideal? And you should be able to answer that. Because we know that lone pairs by themselves push the other atoms away, and we know that double bonds do the same thing. They push other atoms away from itself. Anywhere where there's a lot of electron density will repel other electrons away from it. So that you'll be able to answer. But you know, I'm not going to say, is it 114 or is it 113? Because yeah, I don't know. I just know it's less than the ideal. Yes, you won't have to calculate that. That's a little beyond this particular class.
Okay, thank you.
Yeah. All right. So let's look at one of these. I just posted, or these have been posted. I think the answers are in there as well. If not, I will post all the answers so you can see them. So let's look at, anybody know what this particular, what that's called? SB. It's not really, it's not an atom that comes up very much. It's kind of interesting. It's antimony or antimony, depending on where you grew
It's a
up.
floor.
And it's poisonous. That's where it gets its name. It's it poisons people. I think it was originally named because it was used to poison monks, but that could just be an old chemist's tale. So let's look at that. So SbF5. So let's clear that. So SbF5. So antimony. Anybody want to tell me, so who goes in the middle? We pretty much know antimony is going in the middle, right? Because fluorine never goes in the middle. So we'll just put antimony there and surround it. So here's my antimony. I'm going to put 5, 1, 2, 3, 4, 5 fluorines around it. 1, 2, 3, 4, 5. How many valence electrons does antimony have? So I want to look that up.
5.
5. Mm-hmm. And how many valence electrons? Fluorine, we should pretty much know that by now.
7.
7. So 5 times 7. So we have a total
40.
of 5 times 7, 35, and 5 is 40, right? 40 electrons. Dang, that's a lot of electrons. All right. Let's go. How many are in bonds?
10.
10. So we have 30 electrons left. So I'm just going to go around the outside. So put 6 at each fluorine. And if I'll be darned, that's a total of 30. 6 times 5, that's 30 electrons. So let's see, are there charges on anybody?
No.
No, because antimony has 5 valence electrons, and it's making 5 bonds, so it's happy. And fluorine has 6 lone pairs and a bond, or 6 electrons in lone pairs and a bond, so it's got 7, so it's happy. Now, anyone remember what shape that is?
Trigonal bipyramidal.
Trigonal bipyramidal. Man, good one. So what it's going to look like is this. So we have, these are our axial positions, right? And then we have, and someone was asking me, how do we show, if we're drawing these in 3 dimensions, how do we show atoms coming at us and atoms going away? Well, we just draw a straight line if they're in a plane. If they're coming out at us, we draw a little wedge like this. So that would be, and then if it's going away from us, we sort of do a hatched line like this. So it kind of looked like that. And then these angles, what would that angle be?
$90.
That would be 90, that's right. And what about this one? What would that angle be?
130.
100, what was it?
130?
120. You're really close. 120. 360 degrees in a circle, and we divide by 3. So yeah, it's 120. So it would look like that. Let's see if we're close. Yes. So, ooh, we have like a little ball and stick model in there. Yeah, so it's the classic AX5. So your antimony's in the middle. It's got 5 fluorines around it and has no lone pairs. So it is the classic trigonal bipyramidal shape, and all of the angles would be ideal, 90 and 120.
Professor,
Oh, let me go back.
on the test, did you want us to draw the 3D version or?
I would draw like sort of just like the way I showed you, with the wedges for them coming out and then the hatch marks going back. Or you could draw it like that. I mean, either one, as long as you basically just show me where the atoms are. I mean, it doesn't have to be like, you know, a work of art or anything, but just sort of just get the general shape right, so that you'd be able to, just by looking at it, I would be able to determine, you know, these are axial positions and these are, you know, pyramidal positions or equatorial positions, and that's fine. Yeah. And you should be able to also tell me that the bond angles will be ideal, because all of the atoms are the same. Like each bonding atom is exactly the same. There's no lone pairs, so it should be the ideal situation. As opposed to this one, where just really briefly, you may say, what the hell is this? I got bromine and fluorine? Yes. Remember, yesterday we made a molecule with xenon and fluorine, and xenon is, you know, is a freaking noble gas. And so fluorine is able to take electrons away from a noble gas. It's going to be able to take electrons away from bromine as well. So if we were to draw this, which would go in the middle? Again, not a surprise.
Bromine?
If there's only one of them, it's probably going in the middle. Right, and bromine is less electronegative. Why is bromine less electronegative than fluorine? They're both halogens. They're both in group 7. Why is bromine less electronegative than fluorine?
It has a higher mass. It's increasing.
It has a higher mass, so that's right. You're right. You're onto something. What else?
As you go down the group, it electronegativity decreases.
Yeah, how come?
With the
You're
higher,
right. Why is that?
is it because
Because it's not actually based on mass. It doesn't have anything to do with the mass. It's something to do with something else.
Is it the radius?
Size?
Yeah, it's the size, exactly. And the size and the mass are 2 different things, because the mass, where's all the mass in an atom? Like 99.9999% of the mass is in one place. Where is it?
The nucleus.
It's in the nucleus, right? And we're dealing with electrons. And so the bigger the atom, remember, every time we go down the periodic table, we do a new period, we add another shell of electrons. And so those electrons move further away. So every time the atom gets bigger as we go down, the electron shell gets bigger, the radius gets bigger, and so the nucleus can't pull on those electrons as much because they're further away. So fluorine is tiny. Fluorine is really, really, really small. And so it pulls on electrons very, very well. Bromine's bigger, so it can't pull on electrons as well. And that's why, in this particular situation, bromine is going to be given electrons to all these fluorines. Each fluorine is going to steal one. So, if how many valence electrons does bromine have? Same as fluorine, actually. How many is that?
7.
7. They all have 7. So basically, what we'd be looking at here is bromine would have 1, 2, 3, 4, 5, lone pair, 6, 7. So that would be the structure. So what would be our AXE in this one? How many areas of electrons in bonds are around bromine?
5,
5. And lone pairs?
1.
1. So then, yeah, so this would be the shape we'd be looking up. So we'd look it up, and we would get the octahedral arrangement, because there's 6 regions around. So remember, when there's 6 regions around, it's octahedral. This is not, so the overall structure is octahedral, but the molecular shape itself won't be, because it has the lone pair down here. So our lone pair would go down here. Oh, wait a minute, let me draw. So there's my lone pair down here at the bottom. And that lone pair actually will push these fluorine atoms up a little bit and away. And so instead of it being completely flat, those fluorines will actually be pushed up a little bit. So these bond angles would be a little less than 90 degrees. Okay? Do you see how it works with basically what I want you to take away is, like, if you can figure out how to put these molecules together and then identify which are bonding pairs of electrons and which are non-bonding pairs of electrons, then you just look up the shape. There's no reason to have to memorize all the different AXEs versus shape. There's no reason to do that. You can just look that up. But I will want you to know what effects the lone pairs, the double, the triple bonds will have on the bond angles of those shapes, okay? All right. So let's look when we have more than one central atom. You can see that we can look at the overall shape of each one of them and then get an overall shape for some of these more complex molecules. So this is ethane, which is basically the same as methane, but it has 1 more carbon. So instead of CH4, we have C2H6. So here's our 2 carbon molecules. So we got 2 carbon atoms here. And so each one of them would have a perfect tetrahedral shape around the carbon, because they each have 4 bonding pairs of electrons around them and no lone pairs. So the tetrahedral shape of this would be the same as the tetrahedral shape of that. So that would be relatively ideal. But if we replace one of these hydrogen atoms with a hydroxyl group, and if you remember from the other day, I talked about a hydroxyl group in organic chemistry. It's just an OH group. So now we've replaced it with an oxygen bound to a hydrogen. So this is actually the shape of methanol. This carbon atom is not affected. So all of its bond angles are still going to be around 109 degrees. But this one is going to be different, because we have some lone pairs around the oxygen. It's going to be a little more highly negative on this side. It will actually push a couple of the hydrogens away and affect its shape a little bit, affect the bond angle slightly. So what we can do is we can look at it carbon by carbon by carbon and see what effect the shape has. So we don't have to worry about, if we have this big long molecule, don't worry, we can just look at it one by one by one and see what the effects of the shapes will be. So let's have a look at something else. So what we're going to do is we're going to draw acetone. You've probably heard of acetone. Anyone know where you'll find acetone in your house? You probably got some right now. Probably in your bathroom.
Nail polish remover.
Exactly. Nail polish remover. And acetone is a really good solvent, as we will see, because it has a polar side and a non-polar side. So basically, acetone will dissolve everything. So if it's something aqueous and polar, it'll dissolve that. And if it's something non-polar and kind of organic, it'll dissolve that too. That's why acetone is such a good solvent and why it's used for nail polish remover. So let's draw it, and we'll determine the shape around one atom at a time. So here's let's look at what the shape will be. So we've got a carbon in the middle, double bond to this oxygen, and then we have two what are called methyl groups. A methyl group is just CH3. So it'll look like this. And then over here we have another one. CH3 is just called a methyl group. Basically, it's methane bound to something. So when we look at that, oh, and remember, we're going to have two lone pairs in our oxygen always makes two bonds and has two lone pairs. So that's what it's going to look like. So the question is, what do you think the bond angles are going to be around this one, around that one, and this bond angle here? So what about this particular carbon? Is it going to be, first of all, we do the AXE on it. How many bonding groups does it have around it?
Three, four.
Four. Yeah, it's got four. It's got three hydrogens and it's bond down to another carbon. So it's got four. And since it's carbon, it generally does not have lone pairs. So AX4, that's tetrahedral. So we would expect around 109.5 degrees or so. What do you think the bond angles around this carbon are? Are they going to be close to that?
No,
How come?
because of the double bond from the oxygen.
Yeah, but it's way over here. I mean, it's bonded to that carbon. So it's sort of, it's a distance away. So actually it doesn't have much effect on this particular carbon. We would expect this one and this one to be pretty close to ideal. Maybe not exactly ideal, maybe a degree or two, but pretty close. So my other question is, what about this bond here? What about that one? What sort of angle would we expect for this carbon? So if we were to do AXE for that particular carbon, how many bonding regions are around that carbon?
Two.
No, we've got one more. It's got this one. So there's 1, 2, 3. It's got 3. So it's got two single bonds. Those are each a group. And it's got a double bond. That's a group also. So we'd say it has 3 bonding groups of electrons around it. And it doesn't have any lone pairs. So again, so now we have AX3. And you remember what shape that is? When you have 3 groups?
Trigonal planar.
That's right. It should be a triangle. So this angle should be around 120 degrees. But do you think it's more or do you think it's less?
Should be less.
Okay. Explain yourself.
Because wouldn't the double bond from the oxygen and the carbon pull it?
Pull it or push it? So I'm looking at, basically I'm looking at this angle here. I'm looking at the, whoops, let me get the, I'm looking at this angle, OCC. I'm looking at this particular angle right here. So this one.
Oh, it'll push it.
Yeah, push it real good. That's right. So it'll be a little more than 120 degrees. That's right, because since we have a double bond here, we have more electrons than a single bond. So it pushes it away. So this should be a little greater than 120. Now, let's see if we geniuses are right. And actually it does. See, it doesn't push it much. Doesn't push it real good, but it does push it a little bit. So instead of 120, we get 100, whoops. So instead of 120, we get 122, but it's a little more, so we got that right. And the bond angles around the outer carbons are pretty much, they're not really affected. So they would be pretty close to ideal. They're not going to be affected by this double bond because it's too far away. But it will affect this this angle because it'll push it a little bit. But you see, not by a whole lot, but it does push it a little bit. All right, so we sort of talked about this topic already a little bit, so you guys should be just ready to nail this one. So we talked about why shape and polarity are so important, because we can predict, if we just look at a drawing, if we just do just a basic model, if we look at, whoops, let me go back. If we look at a representation, like if we look at carbon dioxide, we can look at that and we can say, yeah, it has polar bonds. So this is polar going in this direction, and this is polar going in that direction. And you can even say that that those particular polar bonds are equal, but unless we know what the shape of it is, we can't tell if the molecule's polar. We can say the bonds are polar, but we can't say the molecule's polar. And if you remember, I sort of mentioned that you can actually measure the polarity of molecules by what's called the dipole moment. It's right here, the dipole moment in the unit Debbies, which I think is just so adorable. So yeah, so the dipole moment is given mu, the Greek letter mu, and for actual units it's in Debbies, little Debbies. So a molecule is polar when it satisfies two criteria, right? It's got to have a polar bond in it. If it doesn't have any polar bonds in it, you don't need to know anything about the shape. It's not going to be polar. So if it has at least one polar bond, okay, and the individual dipoles, when you add them all together, don't cancel each other out. And that's the case in carbon dioxide, as we've looked at before. Since those dipoles, those bond dipoles, are equal and opposite and pointing exactly opposite each other, they cancel each other out. And so we have a molecule with two polar bonds, but the overall polarity of the molecule is non-polar, okay? So what we're going to do is take that information and convert that over into the shapes we've been looking at. Now, can we look at these more complex shapes and see whether or not we're going to have polarity? And you've already done this. You've done this very experiment in one of your labs. You determined whether or not molecules were polar by flipping the electric field on. So remember, when you changed the angle of some of those molecules, when they were linear, they were non-polar. And the minute you did anyone do this? You just introduce just a slight bend, just a slight bend. It could be just like 2-3 degree bend. And then it sort of all tilts over, reorients itself, and then moves toward either the positive or negative pole, depending on whether it's the positive or negative side of the molecule. So here we've got hydrogen fluoride, and we know since fluorine is hella negative, it pulls those electrons toward itself and makes itself slightly negatively charged. So this side of the molecule has more electron density than that side. And so when we flip the switch on for electric field, they will orient themselves so that the slightly negative side is pointing toward the positive pole. So now so this is what we just talked about with carbon dioxide. And remember, it's the difference in electronegativity. And again, you could just have if you go to ptable.com, periodictable.com, and it gives you all this information. Just have that open when you're doing a test. If we were doing it in class, I would just give you a cheat sheet with all this information on it. And one of them, which is super essential, is the periodic table with all the electronegativities in it. So this shows you very clearly that oxygen we know is really electronegative. It's more electronegative than carbon, certainly. And so these two bonds are really, really polar. So here's our two bond dipoles. And it's really important to remember the difference between bond dipoles and molecular dipoles. The molecular dipole is basically the sum of all the bond dipoles in a molecule, all of them together. Whereas a bond dipole just tells me the difference in electronegativity between atom A and atom B. And do you remember like what the difference needs to be before we call it polar? And who remembers what the difference is? Don't have to have it exactly, but around what difference?
Like
Delta
0.4
electronegativity. What was that?
0.4 and 1.8.
Yeah. Exactly, between 0.4 and 1.8. If it's more than 1.8, what is it?
Covalent.
If it's covalent, if it's less than 1.8. If it's more than
Ionic,
1.8.
ionic.
Yeah, we're talking ionic, gentlemen. That's high. That's a very, very polar bond. In fact, at that point, that electron is no longer shared. It's just jacked. And the really, really electronegative element just keeps it. But here, if it's more than 0.4, we got ourselves a polar bond. So then we start looking at the orientation of all those polar bonds and see, are they pointing in the same direction? Are they pointing in opposite directions? And then by looking at the direction of the bond dipoles, we'll figure out whether or not the molecule is polar. Because here we could see, in one way, you could say, well, this looks like a polar molecule because it's sort of negatively charged on either end and slightly positively charged in the middle. Yeah, but unfortunately, it's completely symmetric. And so when something's completely symmetric, basically it cancels out all those bond dipoles. Symmetries basically make something nonpolar almost by definition. And when we look at water, we can clearly see. I love the Mickey Mouse picture of water with the lone pair of the two lone pairs of electrons. We have even more polar bonds in water because the difference in hydrogen and oxygen is even more than it is for carbon and oxygen. And the whole reason, as I sort of been blathering since we started the class, the whole reason that water is polar is because of these two lone pairs of electrons. If it wasn't for those two lone pairs of electrons, it would be nonpolar. So it's because of those lone pairs that would be up here, contributes to the polarity in two ways. One, these lone pairs are going to be like really, really negative, and they're sort of on the same side of the oxygen. And it makes it even more polar because it pushes those two hydrogens away and actually increases the polarity even more. So that's why water is so polar for both those reasons. The polarity of the bonds is very high. The shape is even more bent than it would be normally. And the presence of those two lone pairs is highly negative. And so it makes one side of the molecule very, very negative and the other side quite positive.
Is it actually positive or just less negative?
No, it's slightly positive.
Okay.
Yeah, it's slightly positive. Because if you think about it, what's happening, what these dipoles actually mean is electron density is being sucked away from this shared pair and this shared pair. And so that electron density is moving away from the hydrogens and closer to oxygen. So now I have increased electron density around the oxygen, making it slightly more negative, and it's pulling electrons away from both of those hydrogens and making them slightly positive. So it's not the fact that they're less negative, they're actually not negative at all. They're actually slightly positive. That's what a dipole does, is it actually makes one atoms slightly positive and the other one slightly negative. That's basically the meaning of a dipole. But yeah, it's a good point. Okay. So here, basically, we have two molecules that are the same shape, but one of them is polar, one of them isn't. And the reason is because one of them is symmetrical and one of them isn't. And so here we have carbon tetrafluoride, CF4. And this other one, we call this trimethyl or trichloromethane. Oh, I'm sorry, it's chlorine, not fluorine. Duh. CCl4. Trichlorocarbon. So, or carbon tetrachloride. So, this is completely symmetrical. Each of those bonds is extremely polar, but they completely cancel each other out because they're all pointing basically away from each other at exactly the same angle. So they just cancel each other out. But all we need to do is just replace one of those chlorines with a hydrogen, and look what happens. Now, this side of the molecule becomes negative, and the top of the molecule becomes positive. And then we introduce asymmetry. It's no longer symmetrical. It doesn't look the same all the way around. Now I have a negative side and a positive side. And so now it would orient itself in electrical field, and this is polar. And that was, but they're exactly the same shape. So that's why we need, well, not exactly the same shape. The bond angles would be slightly different, but the overall shape would be pretty much the same. So that's why we need to take into consideration the dipoles and the shape. You can't just have one and make a prediction about polarity without having information about the other one. Okay, do you see why this would occur? Basically, it's pretty easy to see that like this second molecule is asymmetric and the first one is. And anytime anything's symmetric, that should be like a tip-off saying, oh, that's going to be nonpolar, because you're going to be right. So let's predict the polarity of a couple of these things. We'll do A and C. Because we talked about ammonia a little bit because we were drawing it in the last recitation. So let's we can review that one. So ammonia. So what's ammonia going to look like? Who's going to be in the middle?
Nitrogen?
Yep, sure is. Nitrogen's going to be in the middle because a couple of reasons. It's actually, but why would nitrogen be in the middle? It has a higher electronegativity than hydrogen. Why would we put it in the middle?
Hydrogen can only bond once.
There you go. Exactly. Hydrogen can't be in the middle because when you only form one bond, you can't be in the middle. So even though nitrogen is more electronegative, it goes in the middle. So 1, 2, 3. 1, 2, 3. And I won't go through it, but that nitrogen has how many valence electrons? What group is nitrogen in?
Fifth group.
Fifth group. Therefore,
5 electrons.
5. So it's got 1, 2, 3, 4, 5. So my ammonia is going to look like that. So what shape is that going to be? What group is that going to be in? How many groups, how many electron groups are around the nitrogen?
4.
4. So it's going to be sort of your basic tetrahedral shape, right? But it's A, so it's got 3 bonds and 1 lone pair. So it's not going to be exactly tetrahedral, but it's going to have sort of a general tetrahedral shape. We call this one sort of pyramidal. So is this going to be polar or non-polar? Oh, before I ask that, which direction are my bond dipoles going to be in? They're going to be pointing toward nitrogen or away from it? Remember, this is my bond dipole. Say that a bunch of times fast. That's my bond dipole. So it points toward the more electronegative atom and away from the less electronegative atom. So it points towards who's going to be slightly negative. So which direction is it going to go? Is it going to be pointing toward the nitrogen or pointing toward the hydrogen? Man, it got quiet.
Sorry, what was the question?
Maybe that was the problem. I was waiting for everyone to answer a question they didn't hear. So the question is, we've got 3 dipoles in this particular structure. The difference between, there's a big difference in electronegativity between nitrogen and hydrogen. I think it's around 1.4, I think. And so that's a big difference in electronegativity. So the question is, so these dipoles, the hydrogen-nitrogen bonds, which direction is this arrow going to be pointing? Is it going to be pointing toward the nitrogen or towards the hydrogen?
Where's the
Towards
nitrogen?
the nitrogen.
That's right. Nitrogen is a lot more electronegative. So when I put the dipoles, they're all going to be pointing towards nitrogen. So is this going to be polar or non-polar?
Polar?
It's going to be really polar. Yeah, it's going to be super polar. It's actually a little more polar than water, because instead of with water just has 2 really polar bonds. Nitrogen's got 3, and so it makes it even more polar. Let's have a look and see what we get here. Yeah, so, 3. I thought it was 3.5. Oxygen is an electronegativity of 3.5. So yeah, so it has 3 really polar bonds, all pointing towards nitrogen, and on top of that we've got the lone pair, and so it makes it even more polar. So we have a very polar, negatively charged or partially negatively charged top, and a partially positively charged bottom. Now I'm going to skip that one and go to, yeah, so boron trifluoride. You pretty much should know just by looking at it, it's going to be nonpolar, because boron is 3 valence electrons, right? So when it bonds to fluorine, it's going to be in a complete triangle. It's going to be a planar triangle, and it's completely symmetrical. So by definition, it's going to be nonpolar. But this one will be interesting. Carbonyl sulfide. Now, what carbonyl sulfide looks like is SCO. So it's got sulfur, carbon, and oxygen. Let's see what that will look like. Let's draw it out. So we got carbon in the middle, sulfur on one side, oxygen on the other. So as usual, carbon goes in the middle. So here's my carbon. It's got oxygen on this side, it's got sulfur on this side. So we put our single bonds in there. How many, so we know carbon's got 4 valence electrons, right? So carbon's got 4. How many does oxygen have?
6.
6. And how many does sulfur have? It's in the same group as oxygen.
6.
Also has 6. So I show a total of 16 electrons. So I've used up how many in bonds so far?
4.
Someone said it.
4.
4, right. So I got 12 left. So what I'm going to do is give them all on the outside and see what happens. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what are going to be my charges? Is anybody charged here? Does anyone have like more or less valence electrons than they should? How many valence electrons is oxygen supposed to have?
6.
It's supposed to have 6. And how many does it have in here? How many valence electrons does it have there?
7.
It has 7, right? So its charge is going to be -1. And since sulfur has the same number of valence electrons and looks exactly like oxygen, it's going to have a charge of -1 as well. What about carbon? How many valence electrons should it have generally?
4.
Should have 4. And how many does it have in our particular model here?
2.
2. Uh-oh. Oh man, so it's got a charge of +2. So that's not going to work, is it? Because we have, oh dear, undo. So we have 2 atoms with a negative charge on opposite side of an atom that has a positive charge. That's not going to be very stable, right? So what's going to happen to our electrons on the outside?
It's going to form a double bond on the carbon and the oxygen.
Yep, so these two, oops, let's draw. So these two are going to jump into the middle and form another bond. So that's where those two will go. What about the sulfur carbon bond? So now oxygen has no charge and carbon is down to +1, but it's still charged. So what's going to happen with the sulfur and the carbon?
Or is going to double bond as well.
Same thing, exactly the same thing, right? Because we have a negative charge next to a positive charge. And, that's no bueno. So we're going to move this pair of electrons toward the carbon as well and make a double bond. So we'll get rid of these. So now nobody's charged. Everybody has the right number of valence electrons. Sulfur has 6, oxygen has 6, carbon has 4. Everyone's chill. No one's charged anymore. The question is this going to be polar? So, is the carbon-oxygen bond polar? Anyone have the
Yes.
electronegativities in front of them? Okay, yeah. What are the electronegativities? Lay them on me.
Oh, I don't have the exact electronegativities on me. I just know oxygen's more.
Yeah, oxygen's 3. I know oxygen's 3.5. That one I remember. So oxygen's 3.5. I think carbon's 2.5. I think.
Oxygen is 3.44.
Okay.
Carbon is 2.55.
Okay. And what's sulfur?
Sulfur is 2.58.
Okay. So we've got. Do we have a polar bond here? Do we have a dipole in this? Do we have a bond dipole in this particular molecule?
No.
Okay. I would say we have one.
Yes, well, the carbon and oxygen.
That's right. Yeah, there is no dipole between carbon and sulfur because the difference in their electronegativity is practically nil. So even if there is a little one, it's super tiny. So that is really small. But this one would be much bigger. And so if we add this super, super small one and this much larger one together, our net dipole is going to be like that. So we would say that, yes, we have a polar molecule. What shape is it? What shape would this molecule be?
Linear.
Here?
That's right. That's right. It would be linear. Why is that?
You have 2 bonds.
Not 2 bonds, remember. There's actually 4. Well, we have 2 of something. What do we have 2 of?
Electron densities?
Yes, electron density, 2 bonding regions. And so we have electron density on this side of the carbon. We have electron density on that side of the carbon. They're sort of, they balance each other out and sort of, so that would be like linear all the way across. So it would be linear and it would be polar. Yes, the molecular shape is linear. There's no real polarity between carbon and sulfur. There is between oxygen and carbon. And so, yes, this would be polar. Now, I think I'm going to just wind up here. We didn't even get to chapter 5. We'll get to that tomorrow, which is probably fine. So there's another way that polarity can show itself with pretty much the same molecule. And can anyone tell me what an isomer is? Has anyone heard of the term isomer before? Well, just have a look and see these two things are isomers. What do they have in common?
Is it the same molecular formula, like a different structure?
Yeah,
Or is that something?
I couldn't have said it better myself. Exactly. So, and not only that, not only are they the same structure, they're the same atoms in the same order. And so other isomers can have like completely different chemical properties. The only difference between the molecule on the left and the molecule on the right is that the chlorines, the two chlorine atoms, are on different sides of the double bond. And so think about the shape of each one of those carbons. What shape would they be? So we've got, how many regions of electron density do we have around each carbon?
5.
No, just one carbon, yes, 3, just one at a time. So this carbon has 3 around it, and that carbon has 3 around it. So what shape is that?
Trigonal planar.
Planar, and it's the planar that's key, because these molecules are planar, they're sort of locked in place. And so the molecule on the left basically has the two chlorine atoms on the same side. And we call that cis. When something's in cis, that's chemistry speak for being on the same side of a molecule. We say that it's cis to each other, cis being same, right? So they're on the same side. So they are close to each other. When they're on opposite sides of the double bond, and since there's a double bond, these things are planar, they're sort of locked in place. They don't spin around, they're sort of locked into position. Now the two chlorines are far away from each other, much further away. And they don't interact with each other because of the distance, how far apart they are. And we call that trans, when they're at opposite sides of the double bond. And so one of these molecules is polar and the other one isn't. Just because one of them has two dipoles that point in the same direction, the cis one, because you have the two chlorines on the same side. So those dipoles are pointing in the same direction. When they're in trans, they're pointing in opposite directions and they cancel each other out. So even though they're pretty much exactly the same molecule, the shape of them is different. And so you could actually separate them. You could separate them by distillation. Anyone know what distillation is? When you distill something, what is it you do? Must have heard of distillation. If I want to distill moonshine, how do I do it?
Vaporize it?
Yeah, exactly. You vaporize it, but then the second part of it, you vaporize it, and then you condense the vapor back into liquid. And so we could do that with these two molecules. If we had because like basically when you synthesize them, you would have an equal amount of both cis and trans. They'd just be like you'd have 50% of one and 50% of the other. If you just wanted to have one, what you would do is just heat them up, and the trans isomer would boil first. So the trans, you'd heat them both up, and then the trans isomer would start boiling, and you collect that vapor and then condense it, and you'd have the trans, and what would be left over would be the cis version. So just the shape alone dictates here whether something is polar or whether something isn't. Okay, is that clear to everybody how that works? You guys are doing so much organic chemistry today. I'm so proud of you. So remember, difference of electronegativity, that tells us whether or not a bond is polar. Okay, once we got that information, that'll tell us whether the whole molecule is polar, once we know the shape. That's the key right here. That's the key part of this. Then, I don't know if we're going to have time. I'm hoping that at the end of the term, we'll sort of dip our toe a little bit into the polarity of molecules and how that affects intermolecular forces. Intermolecular meaning the forces that attract different molecules to each other. It's really cool because it helps explain a whole lot of physical properties. It explains solubility. It explains why some things are reactive and some things aren't. Hopefully we'll get to it, but since I babble too much, it might not happen. So I'm going to wind it up there, and we will start on chapter 5 tomorrow.